So in this problem, it tells me I have sodium hydroxide reacting with formic acid. Okay, and it says how much formic acid is needed to reach the equivalence point. So I'm going to really quickly write out this acid-base reactions just so we can see it. So here's my formic acid, and it reacts with a strong base, so that would be OH minus. And so what's going to be produced is your conjugate base, so CO2H minus plus H2O. Okay, so let's make sure I can answer these questions now. How much formic acid is necessary to reach the equivalence point? So I'm going to go, I know the concentration of NaOH, I know the volume, and I know the concentration of my acid. So I'm going to start off with the volume of my base, which is 0.020 once I convert it into liters. I'm going to get that first into moles, so I'm going to multiply by the concentration of NaOH, since the liters cancel. Now I'm in moles of NaOH or moles of OH minus. Based on the reaction I wrote up here, I know for every 1 mole of OH minus, I have 1 mole of H plus, or of my acid, I'll just write. Okay, now I'm in moles of acid. Now I need to figure out the volume of the acid that's needed. So I'm going to put the concentration of the acid on bottom. So moles on bottom to cancel them out, and then 1 liter up top. Okay, and so when I do that math, what I end up getting for my answer, and you don't need a calculator for this, is A. Okay, then it says at the equivalence point, is the solution acidic, basic, or neutral, and why? Well, since we know we have a weak acid here and a strong base, I automatically know that the solution is going to be basic. So I can get rid of A and D for answers. Now the reason why it is basic, let's say I have, since I'm at my equivalence point, I've got equal amounts of acid and base. So let's say, for example, I'm going to throw out numbers here, just 5 molar of my acid and 5 molar of my base. Initially, I don't have any of that of my conjugate base, and I have no water. Okay, so if I'm creating my ice chart here, I know that all of my weak acid and strong base will react, so that means that I'm going to have only the conjugate base left over. And so the answer to this question is B, simply because the only thing that's left at equilibrium is going to be your conjugate base, which is this guy, and therefore the solution will be basic. In 3, it says if the formic acid were replaced with a strong acid, such as HCl, at the same concentration, how would that change the volume needed to reach the equivalence point? If I were to draw the titration curve adding hydroxide of certain volume of hydroxide, right? That's my x-axis, and my pH is my y-axis. If this were for a weak acid being added, right? The only thing that's going to change if I am adding a strong acid to a strong base instead of a weak acid to a strong base is the following. I'm going to start out at a lower pH because I have a strong acid, okay? And your equivalence point is going to be happening at a pH of 7. Okay, so your equivalence point, let's say right here, is going to be 7, while for a weak acid with a strong base would be something higher. It's going to be basic. The rest of this curve all looks the same. So the only thing that's changing is your initial pH and your pH at your equivalence point. For a weak acid, your initial pH is higher and your pH at your equivalence point is higher. The amount of acid or base required does not change based on the strength of the acid. It's always going to be the same amount of acid and base. So your answer will be D. It's important to note that while your pH is going to be different for initially and at the equivalence point when you're using a strong acid versus a weak acid, or a strong base versus a weak base, the amount of each that is required does not change, and that's something important that you need to remember. Okay? In 4, it says, which of the following would create a good buffer when dissolved in formic acid? So remember, in order to create a buffer, I want to have equal amounts of this weak acid here and this weak base. Okay? That will give me a good buffer so that if I add a strong base, this acid can react with it, or if I add a strong acid, this base can react with it. So if I look at these options, this here is a salt. Remember, I ignore Na because I don't care about it. So I'm adding CO2H minus, which is my weak base here. So that forms a great buffer because I've now got my acid and my weak base. So I'm going to put this answer. Let's look at the other options. If I add another weak acid to my formic acid, that doesn't help me make a buffer. NH3 is a base, I agree, it's a weak base, but it has nothing to do with this reaction here. Okay, so that's not going to create a good buffer, and then water's not going to help. Remember, your two other options is you could add to your acid a strong base, but remember, you're only going to add half as much strong base. That could form a good buffer. So like, for example, if I have 5 molar of my weak acid, if I add 2.5 molar of my hydroxide, remember, since the change will be 2.5, what that means is when I'm at my equivalent, when I'm at my equilibrium, when this reaction has occurred, I'm going to have, again, equal amounts of weak acid and weak base, 2.5 and 2.5. So that's a great way of creating another buffer. Or you could take this weak base and add half as much of the strong acid to it. And again, if I wrote out the base dissociation with this and did all of this math, you get the same answer. For number 5, it gives you this reaction. It says the above equation represents the reaction between the base methylamine and water. Which of the following best represents the concentrations of the various species at equilibrium? And so what I notice, my Kb here is 4.38 times 10 to the negative fourth. So that tells me that my reactants are going to be favored. So I'm going to have more of this base than I will of OH minus or CH3NH3, okay? Because my K is less than 1. If my K were greater than 1, I would have more products. So I automatically know that my concentration of CH3NH2 is going to be greater than that of OH minus and its conjugate acid. So all of the answers, A and B, do not work. Now I've got to consider the difference between C and D. If I change by X, right, then this is going to increase by X and this is going to increase by X. Since I started with no OH and none of the conjugate base, that means at your equilibrium, that means that your concentration of OH minus and CH3NH3 plus will be the same. So your answer is D. For 6, it says the following reaction is found to be at equilibrium. Okay, I note my change in enthalpy because I might have to deal with that. What is the expression for the equilibrium constant? Well, I know for my equilibrium constant, it's products over reactants. Okay, and remember, you're going to, if you have a coefficient of 2, you're going to square. So the answer that works here is going to be C. So that's a pretty nice, easy problem for you. Which of the following would cause the reverse reaction to speed up? Meaning, I don't really love the wording here, but what it's basically saying is what would cause a shift to your left. Okay, so let's figure that out. If I add SO3, okay, that would cause a shift to the right, and we can say shift and everything, just don't write it, so that won't work. If I raise pressure, well, I've got 2 moles of gas here, I've got 3 moles of gas here. Remember, if you raise pressure, you're going to shift to the side with fewer moles of gas, right? So then that would work, so B is an option. If I lower temperature, since this is exothermic, that means heat is on my product side here. So if I lower temperature, I would shift to the right, so that does not help. Okay? And if I remove SO2, which is here, I would shift to the right as well. So my answer is going to be B. Remember, you need to be comparing Q and K if you write out an explanation, but if you're doing it in your head, saying shifting is totally fine. Okay, for 8, it says the value of Kc is 8.1. What must happen in order for the reaction to reach equilibrium, so I'm not at equilibrium, if the initial concentrations of all 3 species is 2 molar? Meaning, this is asking me to solve for Q, so let me do that really quickly. So Q is going to be, I'm going to use this equation right here, this expression, so everything is 2. So oxygen's concentration is 2, SO2 is 2 squared, SO3 is 2 squared at all, which means Q is 2. So if I have to figure out what's going on, since my Q is less than my K, what that means is I need to shift to the right in order to have Q equal to K. So I'm going to shift to the right, which means the rate of the forward reaction would have to increase. I agree, because I'm shifting to the right. Okay. However, would that cause SO3 to decrease? And the answer is yes, that would cause SO3 to decrease because I'm shifting to the right. So A works. B does not because it's the exact opposite of A. Both the rate of the forward and the reverse would increase. You can't have both of them increase because if they both increase, there wouldn't be any shift, and you need it. And then for this, it says no change would occur in either the rate of reaction or the concentrations. That's not true. Since your Q is less than K, you need a shift to the right. So your answer would be A. In number 9, it asks, which of the following would cause a reduction in the value for the equilibrium constant? Okay, so remember the reaction that you were given. So we have the 2SO3 produces O2 and SO2. Okay? And so let's look at each of them. So if you increase the amount of SO3, okay, that's going to cause your reactants to increase, which would cause a shift to the right. Okay? And if you're shifting to the right, that would cause your K, your equilibrium constant, to increase. And that's not what we're looking for, so that doesn't work. If we reduce our amount of O2, again, that's going to cause a shift to the right, so K would increase, so that doesn't work. If I raise temperature, since this is an exothermic reaction, that means my heat is on my product side. So if I raise temperature, that's going to cause a shift to the left. And so since I'm shifting to the left, that means my K would decrease, which means that would be my answer. Okay, for number 10, it says the solubility of product, KSP, for AgCl is 1.8 times 10 to the negative 10. So I'm going to really quickly, whenever I see anything about solubility, I'm going to write out the proper reaction. So it's AgCl produces Ag plus Cl minus. Okay? Which of the following expressions is equal to the solubility of AgCl? Well, I know that the solubility is going to be my X. And I know that this is X and this is X. And remember, molar solubility or solubility is your X. So what I want to do is my KSP is going to be equal to X squared. Well, my KSP is 1.8 times 10 to the negative 10th, which means to solve for X, what I have to do is I have to square root this. So my answer is D. For number 11, it tells you a 0.1 molar solution of which of the following acids will be the best conductor of electricity. Well, to be the best conductor of electricity, you want the most ions, which means since all of these are going to be acids, I want the strongest acid because that will produce the most ions, which will make it the best conductor. So my answer is going to be D because nitric acid is a strong acid. In 12, it says, which of the following expressions is equal to KSP for Ag2CO3? So I'm going to really quickly, since I know I'm dealing with solubility product, I'm going to write out the reaction. So that's my solid. That is going to produce 2 silver ions and carbonate, which means that my solubility product is going to be equal to the concentration of silver ions squared times the concentration of carbonate ions. And so my answer, therefore, is going to be, for 13, it says if the solubility of barium fluoride is equal to X, which of the following expressions is equal to the solubility product KSP of BaF2? So again, I'm going to write out my reaction. This is barium ions and fluoride ions. Okay. So this is my X, that's my solubility, so this is X. For fluoride, because it's 2 fluoride ions, it's going to be 2X. So when I write out my KSP, that'll be X times 2X squared, and so what that gives me is 4X cubed. For 14 through 16, it tells you have 100 mils of saturated strontium fluoride solution present in a 200 ml beaker at room temperature, and it gives you your molar solubility, which is your X. It says, what are the concentrations of strontium and fluoride in the beaker? So, I've got to write out my reaction again. So it's going to be strontium fluoride, breaking apart to form strontium ions, so SO2 plus, and 2 fluoride ions. Okay? Since your X is going to be 1.0 times 10 to the negative third, and this is x, that's going to be my concentration of SR2+, so I'm going to get rid of these other two answers. And your fluoride is 2x, which means that my answer for this is going to be B. Okay? In 15, it says, if some of the solution evaporates overnight, which of the following will occur? Well, if some of the solution is evaporating overnight, the only thing that's going to evaporate is going to be water. So you're decreasing the amount of water that it's dissolved in. Okay, so what will that do? Well, if you think about it, this is a saturated solution, meaning the maximum amount of strontium is dissolved as strontium ions and fluoride ions as is possible. So if you reduce the amount of water, that means you're going to form some solid, okay? Because you've reduced the amount of liquid available for these guys to dissociate into, you're going to cause more solid to form. So if you look at the answers, the mass of the solid is going to increase, so I can get rid of C. But keep in mind, if a solution is saturated, what that means is it has the maximum amount of ions dissolved as possible. So the concentration, when it is saturated, will always be 1 times 10 to the negative third and 2 times 10 to the negative third. So since you're losing water, more solid will form, but the concentration of ions in the solution is going to be the same. The reason why the solid precipitated out and formed a solid is because you have to maintain, this is the maximum amount of strontium ions that can be dissolved, this is the maximum amount of fluoride ions that will be dissolved. So as a result, the concentration of the ions is going to stay the same. So my answer is D. In 16, it says, how could the concentration of strontium ions in solution be decreased? Okay, so I'm wanting to decrease the amount of strontium ions. Well, how can I do that? Well, if I were to, add NaF. Well, if I'm adding NaF, what that means is I'm actually adding fluoride ions. So that would cause a shift to the left. If I'm shifting to the left, that would cause the concentration of strontium ions to decrease. So that's an option. If I added strontium to the B group, that doesn't make sense. If I'm adding strontium, yeah, it'll shift to the left, but I've already increased the amount of strontium, so that doesn't make sense. If I heat the solution, well, if you heat a solid, more of it is going to dissolve into solution, because for a solid, if you increase the temperature, it is better able to dissolve. It's better able to saturate your solution. Just think about hot cocoa, so that doesn't work. If I add a small amount of water, but don't dissolve all of the solid. So if I add some water, that will allow more strontium to dissolve, but since I'm also increasing water with the number of ions, the concentration is going to stay the same, since the concentration is ions over the total amount of solution, and I'm increasing both. So my answer is A. For number 17, it says a student added 1 liter of a 1.0 molar potassium chloride solution to 1 liter of a 1 molar lead nitrate solution. A lead chloride precipitate formed, so you form lead chloride, and nearly all the lead ions disappeared from solution. Which of the following lists the ions remaining in this solution in order of decrease in concentration? Well, it says nearly all the lead disappeared, so B and C don't work because lead should be the least concentrated. Now comes a little bit of stoichiometry. So if you think about it, for every 1 mole of potassium I have, I'm going to have 2 moles of nitrate, right? So the concentration of nitrate, if I were to find that, is going to be 2 molar versus just 1 molar for potassium, which means that there's going to be more nitrate than potassium. So my answer is going to be A. In 18, it says a gaseous reaction occurs and comes to equilibrium as shown above. Which of the following changes in the system will serve to increase the number of moles of I2? So I want that to increase. Okay? So if we look really quickly, I've got 3 moles of gas on this side. I've got 3 moles of gas on this side. So talking about volume, that won't help at all since I have equal numbers. If I increase the temperature, that's going to cause a shift to the left, which means my concentration of I2 would decrease, so my answer must be D. In 19, it says the reaction above came to equilibrium at a temperature of 100 degrees Celsius. At equilibrium, the partial pressure due to NOBR is 4 atmospheres. The partial pressure due to NO is 4, and the partial pressure due to bromine is 2. What is your Kp? So remember, Kp, the only thing that can affect it are gases. So I've got the partial pressure of bromine times the partial pressure of NO, because both of them are gases, that needs to be squared, divided by the partial pressure of NOBr, and that will be squared. Okay? Since that is 4 and that is 4, these will actually cancel because they're equal. And so all I'm left with is the partial pressure of bromine, which was 2, so that's my answer. For 20, it says at 150 degrees Celsius, the equilibrium constant Kc for the reaction shown above has a value of 300, okay? Which means that my products are going to be favored. This reaction was allowed to reach equilibrium in a sealed container, and the partial pressure due to IBr is found to be 3 atmospheres. Which of the following could be the partial pressure due to Br2 and I2? So I'm going to write out my Kc really quickly, my expression. So I know it's the concentration of IBr squared all over the concentration of Br2 times my concentration of I2. Now notice the issue with this is they're talking about Kc instead of Kp. And so one thing, I didn't think this needed to be discussed, but it clearly does. Your Kp equals your Kc if you have equal amounts of gas on both sides. So I've got 2 moles here and 2 moles here. So if you have equal amounts of gas on both sides, number of moles of gas on each side, then your Kp equals your Kc. Okay? So instead of this being concentration, which I had thought originally, it should be partial pressure of IBr squared, and the partial pressure of Br2, and the partial pressure of I2. Okay? So now what I can do is I can say, okay, my Kp equals 9 over your partial pressure of Br times your partial pressure of I. Since your Kp is 300, now I just have to do basic math. So the 2 partial pressures times 300 has to equal 9. So what I can do is I can simplify the math of that and say the partial pressure of these 2 multiplied by each other has to equal 9 over 300, which simplified would give me 3 over 100. Which is the same thing as saying 0.03. So your task is to take all of these values and figure out which one would give you 0.03. And the answer to that is that A would. In 21, it says a laboratory technician wishes to create a buffered solution with a pH of 5. Okay? Which of the following acids would be the best choice for a buffer? Meaning I want my pKa be equal to 5 since I'm talking about creating a buffer, and the best buffer is the buffer at your half equivalence point where pH equals pKa. If I look at all of these options, just as a quick math help, this value, if you take 5.9 times 10 to the negative second, and you take the negative log of that, that's going to give you a value since you have a number. So 10 to the negative second would give you 2. As soon as you have a number in front, that's going to give you a value that's slightly less than 2, okay? So this is going to be about 2, but it's going to be a little bit less. This is going to be about 3, but a little bit less. It's going to be about 5, and it's going to be about 8, but a little bit less because you have the numbers in front. Okay, so keep that in mind. And so my answer here is just going to be C. Which of the following species is amphoteric? Amphoteric means that it can act as a base and an acid, meaning which one can accept a proton and which one can donate a proton, depending on the situation. The only one here that can do that is HCO3 minus. Okay? H2CO3 cannot accept. CO3 2 minus doesn't have anything to give. How many liters of distilled water must be added to 1 liter of an aqueous solution of HCl with a pH of 1 to create a solution with a pH of 2? Meaning, I'm going from a concentration of 10 to the negative first to a concentration of 10 to the negative second. So I'm going to use my dilution formula, M1V1 equals M2V2, to figure this out. So I have 1 liter of 10 to the negative first. So then, to get 10 to the negative second for my new concentration, what volume would that have to be? Well, I can do that math pretty easily. I get 10 milliliters. So the question is not what would the final volume have to be to get that concentration, it's how much water would I have to add. Well, if I started with 1 and I need to go to 10, I need to add 9 liters. Okay? For 24, a 1 molar solution of a very weak monoprotic acid has a pH of 5. What is the value of the Ka for that acid? All right, so I need to figure out the Ka. I don't know it, so I'm going to write out a generic acid dissociation reaction. So A minus plus H plus. I know I start with 1 molar of that. I'm icing this. The other piece of information I'm given is that the pH is 5, which means at equilibrium, my concentration of H plus is 10 to the negative 5th. You should be able to do that math in your head, right? So since I start with 0 of hydrogen, that means my change is going to be 10 to the negative 5th here. And I'm going to just say, since 1 minus 10 to the negative 5th is basically going to be 1, I'm just going to keep it like that. So my Ka, when I write my expression, it'll be the concentration of H plus, which is 10 to the negative 5th, times the concentration of A minus, which is 10 to the negative 5th, all over 1. And so my answer is going to be 1 times 10 to the negative 10. 25, the value of Ka for HSO4 minus is 1 times 10 to the negative 2nd. What is the value of Kb for SO42 minus? So remember, Ka times the Kb for the conjugate base equals Kw, which is 10 to the negative 14, when you were at 25 degrees Celsius. Okay? And assume you're at 25 degrees Celsius unless they state that you're not. So here I just need to do math. So this is going to be 10 to the negative 2nd times Kb equals 10 to the negative 14. So 10 to the negative 14 divided by 10 to the negative 2nd. Remember, you subtract your exponents, now it will give me 10 to the negative 12. So I'm going to use the following information to answer 26 to 28. So it says the following curve is obtained during the titration of 30 mils of weak base with a strong acid. Okay, so it says why is the solution acidic at equilibrium? Well, at equilibrium, it is acidic because, remember, I have equal amounts of weak base and strong acid. So I'm going to really quickly write that out just for you to be able to see. Okay. Let's say I'm going to make up a number. Let's say, for example, I like using the 5 molar. So I have 5 molar of weak base, 5 molar of strong acid. At your equivalence point, since you have equal amounts, what that means is the only thing that is going to be left over is the conjugate base of your weak acid. So if you look at all of these here, your answer for 26 is going to be B. For 27, it says, what is the concentration of the acid? Well, I know my volume and my concentration of my base, and I know my volume of my acid. So just like what we did in the lab, let's actually write this out. So I've got volume, I'm going to convert into liters in my head. So that's the volume of my base times the concentration of my base. I know that the ratio is going to be 1 to 1 because they're both the acid is monoprotic and NH3 will react in a 1-to-1 ratio with that. And then, now that I'm in moles of my acid, I can figure out the concentration by simply dividing by the volume. Well, the volume that's required is about 15. Since this is a multiple choice, I'm going to say it's 15. Okay. And so when I do this math, what I end up getting is that this is 2 molar. Okay. What ions are present in significant amounts during the first buffer region? So this is my buffer region right here. And remember, your perfect buffer is when your pH equals your pKa at your half equivalence point. So that would be when you have used a volume of 7.5 mils of your base, because that's half the amount of base you need to reach your equivalence point. Okay. So what's going to be present? Well, if you think about it, if I write out the reaction again, I had NH3, I had H plus producing NH4 plus. So I start off with only NH3 here. I'm adding H plus, but no H plus is going to linger. Instead, it's going to all be converted into NH4. As soon as I hit this equivalence point, I have equal amounts of base and acid, and the only thing that I have is NH4 plus. As I continue to add more H plus past this point, what's going to be left over is now going to be your NH4+, which will stay there, and you're just going to be adding extra H+. So that's why your pH continues to decrease until it just levels off, because at that point you'll be mostly just H+. You'll have some NH4+, but that won't really affect your pH. It's going to be the H+ that takes over. But to answer this question, what's going to be left over? Well, what's going to be left over right now at my buffer, in my buffer region, is going to be my NH3 and my NH4. For number 29 to 31, it says silver sulfate, AgSO4, has a solubility product of 1 × 10 to the negative fifth. The below diagram shows the products of a precipitation reaction in which some silver sulfate was formed. What is the identity of the excess reactant? Okay, so if you think about it, if you look, silver came from something, so some compound was added. It had silver and then something else, right? And you had another compound that was added that had potassium and something else, okay? So what I would predict is that since what you're forming is silver sulfate, what that means is that the anion that came with Ag+ was your NO3, and what came with your potassium is your SO4. So if you look at this, notice there is no SO4 in solution left over, which means your K2SO4 is going to be your limiting reactant because you don't have any excess SO4 2-, which means your silver nitrate, since you've got both of these ions in solution, that means that is going to be your excess reactant. Okay, so just always write it out and figure out where did the Ag come from, where did the NO3 come from, and this is just a double replacement reaction. For 30, it says if the beaker above were left uncovered for several hours, okay, what would happen, right? So if you think about it, the volume of the water will decrease, which means you're going to form more silver sulfate. Because as the volume decreases, since you can only dissolve a maximum amount of ions in solution, some of those ions are then going to become solid. So if you look at these options, it says some of the silver sulfate would dissolve. No, the exact opposite. You're not dissolving more since you're removing water. Some of the spectator ions would evaporate. No, the only thing that evaporates is water. The solution would become electrically imbalanced. No, because you're adding silver and sulfate together. That would be 2 + 1 charges, and this would be a 2- charge, right? And you're removing that from solution even more, so that wouldn't affect charge. Additional Ag2SO4 would precipitate? Yes. For 31, it says, which ion concentrations below would have led the precipitate to form? So as soon as I'm talking about a precipitate, I need to write out my reaction. So Ag2SO4 produces 2 silver ions and sulfate ions. So I know what my KSP is. That was given to me, 1 × 10 to the negative fifth. That's my solubility product right there. Okay. And so what I need to do is I need to plug in values to figure out when, remember if it's asking if a precipitate will form, I need my Q to be greater than my K so that I will have a shift to the left and I will form a solid. So if I look at all these different options, plug in each of these values into your expression. So remember, you're going to have Ag plus squared times SO4 2-. Okay. Plug in all of these values, and the Q you get needs to be less than 1 × 10 to the negative fifth. Well, when I did this, and I did the math for this, when I did A, I got 1 × 10 to the negative fourth. When I did A, I got 1 × 10 to the negative sixth, which is less than K, so that doesn't work. When I did B, however, I got 1 × 10 to the negative fourth. And so that makes Q greater than K, so a precipitate would form. So as soon as you see a question that says, will a precipitate form, you're comparing Q and your K. In 32, it says in a voltaic cell with a copper cathode, and a lead anode, meaning lead is being oxidized in this reaction. Increasing the concentration of lead causes the voltage to decrease. So remember your reaction, I'm going to really quickly write it because I can figure that out, I know it's Cu2 plus Pb produces Cu and Pb2 plus because lead is being oxidized, copper is being reduced. So, if I increase the concentration of Pb2 plus, why would that cause the voltage to decrease? Well, if you think about it, voltage is going to decrease if this reaction, if the forward reaction slows down or does not proceed to the same degree that it should. So, what that tells me is I will have a shift to the left. A shift to the left would correlate with the voltage decreasing. So what would cause a shift to the left? Well, if I increase Pb2 plus, what does that do? Why is there a shift to the left? Well, there's a shift to the left because your Q has increased. And if you increase your Q, it's going to force the reaction to the left in order to reach equilibrium, to reestablish equilibrium, which is going to cause your voltage to decrease. So your answer is A. Okay. For 33, I don't like this question, but we'll talk about it. It says, which of the following could be added to an aqueous solution of a weak acid to increase the percent dissociation? So I have HF, and it reacts to form H plus and F minus. So how do I cause a shift to the right? Because I'm wanting to increase the percent dissociation. I had thought that if you add a base, either NaOH or NH3, that would cause this concentration to decrease, which would cause a shift to the right. So I was going to say add a base. What they're looking for is for you to recognize the fact that by adding water, which is not in this overall reaction, by adding water, you're going to shift to the side with more moles of ions. So it's going to cause a shift to the right. And so that's why they put B. So we've talked a lot in this class about the fact that your pH, your pOH plus your pH equals 14, and all of those different values only if you are at 25 degrees Celsius. So what if you're not? How would that affect you? So let's look at that. Okay? So the reason why your pH is 7 at 25 degrees Celsius is because water is going to auto-ionize, meaning it's going to form H3O plus, right? This water can give a hydrogen to that water. And the other thing that's going to form is OH minus. Okay, so that's something new. Don't freak out about it. But the whole point of this is saying the concentration of H3O plus times the concentration of OH minus equals 10 to the negative 14th when I'm at 25 degrees Celsius. If you think about it, if I look at all these different options, okay, I know that pure water is not always a pH of 7. We had gone over that. The volume would have to change in order for an ion concentration to change. No, I could change temperature, which is what I'm doing. Okay? It will increase because the concentration of H plus is increasing. Well, if the pH increases, that's because the concentration of H plus is decreasing, not because it's increasing. So your answer is D, but let's make sure we understand this. Since this is an endothermic process, my delta H is going to be on the reactant side. This is going to proceed to the right, which means the concentration of this and the concentration of this is going to increase. Makes sense, right? So keep that in the back of your head if you ever see another question about pH at a higher or lower temperature. If it were lower, it would have proceeded to the left and these concentrations would have decreased. Well, how is that going to affect your pH? Well, if both of these increase, specifically if your concentration of H3O plus increases, since your pH equals the negative log of your concentration of H3O plus, if this increases, that's going to cause your pH to decrease. Okay? So that's why when you increase temperature, your pH decreases. Okay? If you decrease temperature, since this is endothermic, your pH would increase. So just keep in mind that when you're at 25 degrees Celsius, your pH of a neutral solution of just water, pure water, is 7. But that is not the case when you are at a higher or a lower temperature. So for the free response number 1, it says the value of the solubility product, KSP, for calcium hydroxide is 5.5 times 10 to the negative 6. Write the KSP expression for calcium hydroxide. Okay? So I would write out my reaction. So I would write calcium hydroxide produces calcium ion, so Ca2 plus 2OH minus, just like what we did in class. And so your expression would be KSP equals the concentration of Ca2 plus times the concentration of OH minus squared. In B, it says, what is the mass of calcium hydroxide in 500 mils of a saturated solution? Well, I first have to calculate my X, all right? And so since I wrote out my reaction quite nicely, I know the concentration of Ca2 plus is X, concentration of OH minus is 2X. That gives me 4X cubed equals my KSP, which is 5.5 times 10 to the negative 6. Now, they rounded to 1 sig fig. I disagree with that. It should be 2 sig figs. So I got 0.011 molar. So that's my concentration. Now I need to find the mass of calcium hydroxide. So I'm going to multiply by the volume, which is 0.5 mils. That now gives me 1 sig fig for my final answer. Okay? And so now I'm in moles of calcium ions. Well, for every 1 calcium ion, there's going to be 1 mole of calcium hydroxide. So 0.005, I got 0.0056 because I didn't want to round too much. That is the moles of calcium hydroxide as well as just the moles of calcium ions. Now I'm going to multiply by the molar mass of calcium hydroxide, which is 74, and that gives me the mass. I rounded to 1 sig fig, so I got 0.4 grams. In C, it says, what is the pH of the solution in B? Well, if I know the concentration of my calcium ions, they got 0.011, I got 0.011, then I know the concentration of OH minus. It's got to be 0.022 because it's a 2-to-1 relationship. Then all I have to do is take the negative log of 0.022, and then I'm going to do 14 minus that, and what I end up getting is 12.3 for my pH. In D, it says if 1 mole of hydroxide is added to the solution in B, what will be the resulting calcium ion concentration? Assume that the volume does not change. Well, if I'm adding 1 mole, what that means is I'm really adding 2 molar of OH minus. So if you look at your KSP, you've got calcium ions, concentration of calcium ions times your concentration of hydroxide ions squared. My KSP stays the same. I'm calculating Ca2 plus. So I actually disagree with what they wrote. So I agree at the beginning. It's KSP equals your calcium ions, so X or Ca2 plus, times your, now what you added, which is your 2 molar, plus 2X, because you added 2 molar to the 2X, and you're going to square that whole thing because you need to square it for your expression. Now, using the rule of 100, you can get rid of the 2X, and then their work works. But I don't like the fact that they just said 2. That's a little bit misleading. And so what you should get is 1.4 times 10 to the negative 6 for the concentration of calcium ions. All right, so I'm going to go over number 2. It says for sodium chloride, the solution process with water is endothermic. So remember, heat is going to be on your reactant side. For A, it says describe the change in entropy when sodium chloride dissociates into aqueous particles. All right, so I told you guys if you're just now on Big Idea 6, you don't need to know this. If you're reviewing for the AP and you've already gone over Big Idea 5, I'm going to quickly explain this. So remember, entropy is a measure of disorder. So if you are dissolving salt into water, you're increasing disorder, which means that the entropy would increase since you're increasing the randomness in the system. Okay. For B, it says 2 saturated aqueous sodium chloride solutions, one at 20 degrees and one at 50, are compared. Which one will have a higher concentration? Justify your answer. So since this reaction is endothermic, if you increase the temperature, that will cause a shift to the right. Now notice, we don't want to be talking about shifting left, shifting right. And so instead, what I'm going to say is, even though they say shift to the right, what I'm going to say is when temperature increases, since this is an endothermic reaction, that causes Q to be less than K. And therefore, the reaction will proceed towards the products, since Q is less than K. All right? And while B was basically telling you, hey, you're increasing the temperature, in C, it specifically says, which way will the solubility reaction shift if the temperature is increased? Well, it's going to shift to the right, as we noted, because if it's an endothermic reaction and you increase temperature, that's going to cause your Q to be less than your K. So it's going to shift to the right. So honestly, I think B and C are practically the same question. All right. Finally, for D, it says if a saturated solution of sodium chloride is left overnight and some of the solution evaporates, how will that affect the amount of solid sodium chloride? Well, since
I've got a saturated solution, which means I've got the maximum amount of ions dissolved. If I decrease the amount of water available, that means that I'm going to have more solid present, because once you're in a saturated solution, if you decrease the volume, that will decrease the amount of ions that are dissolved, right? Because I can't increase the concentration by simply decreasing volume, because I'm already saturated, meaning I've already reached the maximum amount of ions that can be dissolved. So if I get rid of any of the water, I'm going to also have to cause some of those ions to leave solution.
In 3, it says a student tests the conductivity of 3 different acid samples, each with a concentration of 0.1 molar and a volume of 20 mils. The conductivity was recorded below. So what exactly does that tell us? Well, a new concept for you to know: the more ions you have in solution, the more conductive your solution is, the better it is at conducting electricity. So if you look at this, between sample 1, 2, and 3, 3 is going to have the most ions. So if I'm comparing HCl, H2SO4, and H3PO4, I might be tempted to say, well, H3PO4 is going to have the highest conductivity, but it's not going to. And it's not going to because H3PO4 is a weak acid, which means it's not going to dissociate completely, which means it's going to have the lowest conductivity. So that would be 2. Now when I compare HCl and H2SO4, which are both strong acids, now because H2SO4 produces 2 hydrogen ions and 1 sulfate ion, while hydrochloric acid only produces 1 hydrogen ion and 1 chloride ion, H2SO4 will be sample 3 because it has the highest conductivity. Okay? In B, it says the HCl solution is then titrated with a 0.150 molar solution of weak base, and it gives me my Kb. Write out the net ionic equation. This is really nice and easy. I know it's a strong acid, so it's going to be H plus reacting with my weak base, which is CH3NH2, and that's going to produce CH3NH3 plus. Make sure, be careful with your charges. In II, it says determine the pH of the solution after 20 mils of methylene has been added. Well, I know my concentration of my acid, I know the volume of my acid, I know the concentration of my base, and now I know the volume of my base. So the first thing I need to do is define the new concentration of the hydrogen ions and my weak base. Notice what they do here is they just solve for moles, and then they'll go and divide by the volume in the end. I don't like doing that just in case you might forget. Okay, so I would take the 0.0020 and the 0.0030 moles and divide by the total volume, which in this case would be the 40 mils. Okay, so you'll end up with the right answer. Okay, notice what's left over when you do all of this. What's left over, you should have 0.025 molar of the CH3NH2 and 0.050 molar of the CH3NH3 plus. So you can either write out the entire reaction having CH3NH2 on one side and CH3NH3 plus whatever's left over on the other side, or you can just use Henderson-Hasselbalch. Now don't get confused by what they wrote here. Notice they have POH. So what I would have done is said pH equals pKa plus the log of base over acid. And when you do that work, ignore their work, but you should just get the same pH as they did, which is 10.34. I'm not sure why they did POH when you're solving for pH. It seems kind of silly to me. Okay. For number 4, it tells you when the reaction above took place at a temperature of 570 Kelvin, the following equilibrium concentrations were measured. So you have NH3, N2, and H2. Write the expression for Kc. All right. So for Kc, I've written my expression and calculate it. You can calculate it and you get 10. B, we haven't done yet. That's big idea 5, which we'll do at the very beginning of next semester. In C, it says describe how the concentration of H2 at the equilibrium will be affected by each of the following changes to the system at equilibrium. So if I increase my temperature, since this is an exothermic reaction, my delta H is going to be on the product side, which means if that increases, I'm going to see a shift to the left, which means my concentration of H2 would increase. And what I would like to see in your explanation would be it increases because Q is greater than K. In II, it says the volume of the reaction chamber is increased. Well, since I have 4 moles of gas on my reactant side and 2 on my product side, what that tells me is if I increase the volume, I'm going to shift to the side with more moles of gas, which tells me I'm going to shift to the left. So my concentration of H2 is going to increase because Q is greater than K. Don't get overwhelmed by all the other stuff that they talk about, it increasing and then it going back. Ignore that. You don't need to go into that detail. N2 is then added into the reaction chamber. So if I add N2, my Q is now going to be less than K, which means I'm going to shift to the right. So since Q is less than K, my concentration of H2 would decrease. And then finally, if I add helium, that would have no effect because Q equals K. In 5, it says in an acidic medium, iron ions will react with thiocyanate to create the following complex. Initially, the solution is light yellow due to iron, but then it turns golden yellow. So if it's golden yellow, we know there's more iron, more of the complex ion. If it's light yellow, then more of just the iron. Okay. The student creates 4 solutions. They're creating a Beer's law graph, right? So for A, it says on the axis below, create a Beer's law calibration plot. So remember, for a Beer's law, absorbance is going to be on your Y, concentration on your X. You can graph that easily. The slope of the best fit line, okay, is 879, and the y-intercept is negative 0.024. Write out the equation, so it's going to be y equals 879x minus 0.0240. Now, since the equation for the Beer's law curve is supposed to be just a equals abc, technically you're not supposed to have a y-intercept, but this isn't a perfect world, and there's going to be some error in our data. Next, it says to determine the equilibrium constant for the reaction, a solution is made up in which 5 mils of 0.0025 molar iron nitrate and 5 mils of 0.0025 molar potassium thiocyanate are mixed. After 3 minutes, the absorbance is found to be 0.134. Using the best fit line, calculate the concentration. Well, you'll just plug in the 0.134 in for your y, and you solve it, and you should get 1.80 times 10 to the negative 4th molar. Then it says calculate the concentration of iron ions and thiocyanate at equilibrium. Okay? So I know when I add the 2 solutions in this problem, I know I have to figure out their new concentrations. Okay? So what I get for both of them is 1.3 times 10 to the negative 3rd. Okay, that's their initial. And it's asking at equilibrium. So that's a good sign to tell you, hey, you're going to have to use an ice chart. Okay? Now, the important thing for you to know is I don't know my X at first until I look back at BI and realize it asked me to calculate the iron thiocyanate complex concentration at equilibrium. So the 1.80 that you got times 10 to the negative 4th, that is your equilibrium concentration for FeSCN2+. And therefore, that is my X. And so I get all of my values at equilibrium. Okay. Now what I can do is just plug it into my KEQ, and what I get is 150. For C, it says, after equilibrium is established, the student heats the solution and observes that it becomes noticeably lighter. Did heating the mixture increase the equilibrium constant, decrease it, or have no effect? So if it gets lighter, what that means is that iron ions are now, for some reason, being produced more, which means my system must have shifted to the left. Therefore, since I'm shifting to the left and I'm heating it, what that tells me is that my equilibrium constant is decreasing. And it can decrease only when you change temperature, and there I am changing temperature. Okay? Is it exothermic or endothermic? Well, when I increase temperature, I shift to the left. That tells me that this is going to be an exothermic reaction. For 6, it says a student titrates a weak acid with some sodium hydroxide, okay, and it shows the reaction above. Which chemical species present in solution dictates the pH of the solution in each of the volume ranges? So from 1 to 14. So this is before I'm at my equivalence point. So when I'm between 1 and 14, I start off at the very beginning with absolutely no hydroxide and only HA. Okay? But then I start adding OH. So between 1 and 14, what's present is HA and its conjugate base. There is no OH minus because it's all used up. So what's going to dictate my pH? Well, HA and A minus. 15 is my equivalence point, which tells me that the only thing that's going to be present, since I have equal amounts of HA and OH minus, is going to be my A minus. So A minus is what's going to dictate that one. Then from 16 on, I have the A minus, but then I'm going to just keep adding hydroxide, which means I'm going to have A minus and OH minus. Which of those is really going to dictate the pH? Well, the strong base, the hydroxide. In B, it says, at which volume is the concentration of HA greater than the concentration of A minus? Well, at my half equivalence point, I have equal amounts of HA and A minus, which means I have more HA before that point. So between 0 and 7.5, which is my half equivalence point, I have more HA than A minus. My HA equals my A minus concentration at 7.5, and then from 7.5 onwards, HA is going to be less than A minus. For C, it says, at which point in the titration, if any, would the concentration of the following species be equal to 0? Justify your answer. You might be tempted to say, once you are past your equivalence point, your concentration of HA will become 0. Here's the problem. Whenever you have A minus in solution, or whenever you have HA in solution, you actually do have a little bit of the other, because HA just in water will produce a little bit of A minus, and A minus in water will form a little bit of HA. So no matter what, those concentrations will never be 0, because you will always have just a little bit. Now, are we focusing on it, and do we talk about it when we look at the different regions? No, but that doesn't mean that there isn't any of it. We just don't tend to talk about it. But because as soon as you have HA, that means you have at least a little bit of A minus, that it's never going to be 0. For D, it says, if the titration were performed again, but this time 2 molar of NaOH were used, name 2 things that would change. Okay? So the first thing, if I double my concentration, what that means is I'm going to reach my equivalence point at a volume of only 7.5 mils of NaOH. Because remember, your equivalence point is when your moles of acid equal your moles of base. So at a volume of 7.5 mils, I would be at my equivalence point. So that's one thing that changes. The other thing that changes is that your pH at the very end is going to be higher, because if you're adding concentration of 2 molar NaOH instead of 1 molar NaOH, when you're left with basically just NaOH at the end, your pH can be calculated by taking 10 raised to the negative whatever your concentration of OH minus is. That'll be your POH, and then you can figure out your pH from that. So the 1 molar NaOH would be 10 to the negative first, so 14 minus that. For 2.0 molar, it would be 14 minus 10 to the negative second. So it's going to be an even higher pH. For the final problem in 7, it says a student performs an experiment to determine the concentration of a solution of hypochlorous acid. The student starts with 25 mils of the acid and titrates it against sodium hydroxide with a concentration of 1.47 molar. The equivalence point is reached after the addition of 34.23 mils of NaOH. Write the net ionic equation. Easy enough. Weak acid with a strong base produces OCl minus and water. What is the concentration of HOCl? Well, I can determine that at my equivalence point. Okay, so what I would do, they don't show the stoichiometry of it, but what I would do is I would take the 34.23 mils, convert that to liters, so 0.03423 times 1.47. It's a 1-to-1 ratio, and I would write that. Now I'm in moles of HOCl, and I can divide by 0.025, and that gives me my concentration of HOCl because I'm at my equivalence point, so the concentration would be 2.01. For C, it says, what would the pH of the solution in the flask be after the addition of 28.55 mils? Okay, so notice I'm not at my equivalence point. So I have to do an ice chart because I'm now just reacting HOCl with NaOH. Okay, so they wrote their reaction here. HOCl plus OH minus produces OCl minus and H2O. Okay, I ignore H2O. I have to find my new concentration of HOCl and OH minus. Again, notice here they're doing moles and then they divide by their total volume at the end. I personally would just do concentration in the beginning. Okay, and so what you should get for HOCl is 0.15 and for OCl minus 0.784. Just make sure not to overround. Since I have weak acid and weak base present, I can just use pH equals pKa plus the log of my base over my acid, and I solve that and I get 8.2 for my pH. For D, it says the actual concentration is 2.25. Okay, so I underestimated the concentration of HOCl. So discuss whether or not each of the following errors could have caused the error in the results. So the student added additional NaOH past the equivalence point. So they added too much NaOH. If they did that, they added too much NaOH, then that would cause the experimenter to assume, since the volume of NaOH is too high, that would make the experimenter assume that the moles of NaOH is higher, which means that the moles of HOCl are too high, which means that the concentration of HOCl, it would cause them to calculate it to be higher than what it should be. Well, that's not what happened. They actually calculated it to be too low, not too high. So that one doesn't work. For II, it says they rinsed the burette with distilled water, but not with NaOH. That would dilute NaOH, forcing you to use too much NaOH, causing you to get a concentration for the acid that's too high. Again, that's not what happened. That doesn't work. In III, it says the student measured the volume of the acid incorrectly. Instead of adding 25 mils of HOCl, they only added 24 mils. So if you think about it, if they only added 24 mils, that means that less of the sodium hydroxide was needed to react, which means since they use less sodium hydroxide to reach their end point, what that means is that their calculated concentration of the acid would be too low because they're assuming that less NaOH is needed, therefore the concentration of the acid is going to be lower than it really should be. And so that is consistent with what they got, specifically the fact that they got a concentration of acid that's lower than it really should be.